Good afternoon, everybody. Thank you very much for being here. This is another session of our QRC seminar. Today, we have the pleasure of having Professor Fabio Sciarrino from the Sapienza University of Rome. Fabio is full professor at the physics department of the University of Rome, La Sapienza, and he's also a senior research fellow at the International School for Advanced Studies, Sapienza. And he's the principal investigator of the Quantum Information Lab in the Department of Physics in Sapienza. And his main expertise is experimental quantum optics, computation, quantum information, and of course, foundations too. I should also mention that Fabio is an ERC grantee. He recently was awarded an advanced ERC grant, and he's one of the main authorities worldwide in photonics quantum information. So I'm very, very happy to have him here in our seminar. And before I give him the word, please remember that you can make questions during the talk if you click on the raise hand icon, or if you prefer, you can also write down your questions in the Q&A icon, and then I will read them in the end, right? But if you want to interrupt the speaker during the talk and raise your hands, you can do it, right? I will be moderating that, but you can do it, so that's fine. So Fabio, thank you so much for being here again, and it's a pleasure to have you here. So please, go ahead.
Thank you, Leandro, for the invitation. Thank you for the introduction. It's a great pleasure to be with you virtually, at least. Hopefully also soon, I would love to come there. So my goal of today is to provide you an introductory presentation on the activities that we've been doing in the last few years on integrated photonics platform. And the goal is to discuss how the achievement of quantum advantage and quantum supremacy. So any question is always very welcome at any time. So please feel free to interrupt me for any curiosity, any clarification, anything will be very welcome. I will start with a very introductory, and then I will start focusing on what I've been doing. But I would prefer to really start from a broad view and then focus on what we are interested in. So I will start from a quantum computation perspective. And the goal is to expand the quantum boundaries from a computational perspective. So this is an outline of my talk. I'm going to describe the concept of quantum supremacy. We will then discuss the photonics approach, boson sampling. I will review the different implementation of boson sampling. And finally, I will conclude with the perspectives. That's our journey that we will carry out in the next 45 minutes. So let me start with something on quantum computation. We know the expectation on the power of quantum computing. We know that we have different complexity class. We know that there are problems that are strongly believed to be hard classically, but are easy for quantum computers. But we also know that the power of quantum computing is limited. But this is not somehow a prediction from a theoretical perspective. Now, the key question, what we can carry out experimentally in the lab? Could we observe a departure between quantum and classical computational capabilities? This is a question that we will try to address together in the next hour. We know the large challenge of quantum computing. We would like qubits that must interact strongly with one another in order to elaborate information. We would like to have qubits which should not interact with the environment, and we must have full control of the interaction between the qubits and the full measurement capability. And somehow these requirements are somehow have some kind of internal contradiction, because you would like to have the isolation fully under control, but you also would like to have the capability to change how information is elaborated. And then we know that there is a key question: how do we address noise? We know that there are several sophisticated schemes to carry out quantum error correction, but we also know that to scale the hardware, errors must be below some threshold. And this implies a very large overhead in the number of qubits and number of gates. This is something that nowadays involves a large number of research centers all around the world, and also large companies are deeply investing in this direction. So now we would like to focus a bit what is the challenge that we would like to address. We ask ourselves, can a quantum system be engineered to perform a computation in a large enough computational hyperspace and with low enough error rate to provide a quantum speedup? And more specifically, can we formulate a problem that is harder for a classical computer, but easy for a quantum computer, and then implement it in the lab? So this brings us to the concept of quantum supremacy, which is something that we have seen many times in the last couple of years, I would say. The term quantum supremacy was introduced by John Preskill now in 2011. That's a tweet by Preskill, which says proposed quantum supremacy for controlled quantum systems, surpassing classical ones. So somehow my comment is that quantum supremacy is a definition for experimentalists, because theoreticians are quantum superior, they do the calculation and it's done. But now, can we move in the lab and can we keep these capabilities running in the lab, taking everything into account? And that's the big challenge. So I would suggest you this excellent review paper written by Aaron Montanaro from 2018. The title is Quantum Computational Supremacy. There are two computer scientists, and then they approach this problem from a computational perspective, but they really provide a very excellent summary on all the caveats that you need to address when you address such a challenge. And we will see in the outline, they comment, a key milestone in this field will be when a universal quantum computer performs a computational task that is beyond the capability of any classical computer, an event known as quantum supremacy. And this is something which is very fundamental, because somehow demonstrating a quantum supremacy, we say without loophole in the final way, will be the demonstration that you have a departure between quantum computation and classical computation. So from my point, it's somehow kind of analogous to Bell inequalities. When you violate Bell inequalities, you can now divide what theory can be described by local eigenvariables and something which violates it, like quantum mechanics. And here it's somehow analogous, but now not from a fundamental perspective, but from a computational one. So you can imagine the extended Turing thesis, which tells us that everything feasibly computable in the physical world is feasibly computable by a probabilistic Turing machine. This extended thesis tells us that all the Turing machines are equivalent up to polynomial resources. And now if you're able to carry out an experiment demonstrating quantum supremacy, you are demonstrating that this conjecture is no more valid because your quantum hardware is now a new class of quantum Turing machine, which is cannot be transformed with polynomial resources to a Turing machine. And this is something which is a key turning point from a technological and scientific point of view. And it's not trivial. It's not trivial because you want to compare yourself with the classical hardware, which has been developed now since decades, and also because I've seen that's the impact of noise, the coherence. So we see really as this is a fundamental question, and this represents a milestone that you need to address fully before you can have universal quantum computer that can have an impact on the society from an economical perspective. So you see, let me again refer to this text, really to provide you, as a goal, quantum supremacy is unlike most algorithmic tasks because it is defined not in terms of a particular problem to be solved, but in means of what classical computers cannot do. So when you want to do quantum supremacy experiment, you want to compare your hardware with a classical hardware. And this raises many, many questions from different perspectives. It's not enough to solve a problem. You also should ask yourself, what happens to the same problem when I have a classical device? So let me try to derive what are the 4 ingredients that you need to carry out an experiment of quantum supremacy. First, you need to identify a computational problem whose complexity scales exponentially with classical hardware, but only polynomially when using quantum devices. Why? Because you really want to have a different scaling so that when your quantum is over classical, the departure between the two grows very fast. Second point, classical benchmarking. You need to take the same problem with a classical hardware. You need to find what is the best classical algorithm in order to find the threshold that need to be beaten to claim a quantum supremacy or quantum advantage. And we come back now to what the different wording of supremacy and advantage. Third, you need to have an experimental implementation. You need to implement this experiment. You need to implement a quantum instance on a system which is large enough to overcome the classical threshold. And finally, you need to validate your outcomes. You need to develop suitable tools to validate the correctness of the output.
Could I ask a question? It's more
Please.
Super. So my question would be, when you do this comparison to a classical computer, do you do this in a kind of heuristic way where you say, hey, I have certain algorithms for my problem and I know how they scale classically? Or are there certain algorithms where you can really prove that it's impossible to do better on a classical computer? Right? Because those, I would say, are different things, because I could imagine if you are clever, you maybe find a different algorithm which runs on a classical machine, but which solves the problem much faster on a classical machine, or have mathematicians or theoretical physicists also taken this task and showed really absolutely that a certain task cannot be faster on a classical machine.
Thank you, because the question is extremely relevant, and the history of the last 2 years tell us as much is relevant. And we'll comment on that later on with a more technical answer, comparing to the Google experiment and the Boson sampling. But let me start with a general answer to your question. Suppose that you have 2 points. The first point is about the scaling. You only try, I will show you Boson sampling as a benchmark. You take a problem and you say, I want to demonstrate that this problem scales bad with a classical computer. And we will see that you can do this with a very general approach. You can show, that's a paper by Prof. Aronson, that boson sampling requires exponential resources when you use a classical hardware. But this does not fully answer to your question, because you say, yes, but now when we compare, which algorithm are we taking? Are we taking the better? We know, yes. And that's a key point, because maybe today, you take an algorithm which is performing boson sampling not so well, but then someone more clever come out and find a better algorithm.
Exactly.
Because the scaling of the classical is still exponential, but the threshold where you have the boundary of quantum supremacy has not been overtaken. So you're perfectly right, and that's what happened with Google, IBM, and the new paper recently. They find some threshold, but then computer scientists are smart enough to improve the classical simulation. And by improving the classical simulation, they are increasing the threshold. So this was the first answer. I will come back to your question when I will have a more specific example to consider. But I hope at least I give you an intuition.
Great. Yeah. Super.
So now let me come back to the name. So you may have noticed I'm using the term quantum supremacy. But this term was a bit criticized because supremacy has also a bad political meaning. And this is why there was a large debate, and it was proposed to use the term quantum advantage instead of quantum supremacy. That's, you see, editorial on Nature, I'm quoting, and there was also a long debate. There was a long post on Aronson article. There was an article on Wall Street Journal on that. And there was a lot of tweet going on that on this discussion. So today, in my talk, I will consider quantum supremacy as a synonymous of quantum advantage. In the previous meaning, someone thought that quantum advantage was a quantum supremacy plus money. That is, I have quantum supremacy and I can also take some commercial benefits. Today, my definition of quantum advantage is exactly equal to quantum supremacy. I don't know if there was some other question. I see a raised hand, maybe. I don't know if I was right. If not, I'm proceeding. So if you, let's again be back to the review I cited before. This review on it, I guess there is a raised hand by Luigi Amico. I don't know if we would like to have a question now.
Yes, actually, I think the question was just right after the René question. So I think I lost the precise difference between your definition of quantum advantage and the quantum supremacy. This is the question. And the second, I think, is a comment on what you discuss about optimization algorithm. Basically, it's very similar to what you obtain in this when you classify the complexity in the complexity classes. Basically, this classification is constructive. So once you have an algorithm, then you can test whether it's a P or NP. So all this optimization problem is always in this computer science constructions. Okay. But anyway, can you please repeat the difference between the quantum advantage and the quantum supremacy?
Thank you, Luigi. So let me clarify. In my talk, I will take advantage exactly equal to supremacy.
Okay.
That means the same. Only for the sake of completeness, I wanted to integrate that some other consider quantum advantage as some of the regime where you have quantum supremacy, but you are also solving something, let's say, useful. But that's a very vague definition. So I stick with the definition quantum advantage is equal to quantum supremacy.
Okay.
Thank you.
Thanks
also for the comments. That's something on which I fully agree. We'll come back then later on also on that again.
Thank you.
So going back to the review I cited before, the review addressed two main platforms that have been adopted to demonstrate quantum supremacy. One is boson sampling, and the other one is random quantum circuits. Today we are going to focus on boson sampling. I will describe in detail what is boson sampling, while random quantum circuits is an approach which has been undertaken by Google. And to describe it in a very simplified way, is somehow the circuital equivalent of boson sampling. Boson sampling does not deal with qubit, it deals with single photons that propagate, we will see, while random quantum circuits address the implementation with qubit. What are the platforms? So this is a kind of summary slide taken by a Twitter account by the Society Pascal using Rydberg atoms, which summarizes the current platforms and worldwide effort in quantum computing. You see all the words are in French. And you see now, I've shown you, I highlighted to you what are the two platforms we will see today. One is the photons on the right side, which is a platform adopted to carry out boson sampling, while in red, you may find the platform adopted for the random quantum circuits. I will only at the end very briefly comment on that to provide you a complete picture, but now my talk will really focus on the photonics implementation. This was my introductory, then we will start zooming on what we can do. So let's start defining what is boson sampling. And this problem was introduced by Alex Akipov and Scott Harrison in 2011. And their philosophy was, in order to demonstrate for the first time quantum supremacy, we should find a problem which is inherently easy to address with a quantum hardware, but which is harder to address with a classical approach. And the idea is the following: is to take n bosons, we will consider n photons, photons which are indistinguishable, not interacting. These photons propagate over a large number of m optical modes, here represented at the center. You may imagine this as many waveguides where light is propagating. So you send the bosons, they propagate, and your goal is to sample from the output state. Then I will also show you a video to give you an impression of what really implies sampling in the lab. It means you don't want to calculate the output wave function. You simply want to sample to generate events which are distributed according to the output distribution of the following dynamics. That's why it's named boson sampling. And the problem that Google addressed with random quantum circuits is similar. We are now sampling not from photons which evolves on an array of m optical modes. When you implement random quantum circuits, you are sampling from qubits which have a random evolution. So let me specify that also in this case, the N bosons evolves in this large array of optical modes, and this evolution is random. There is no specific symmetry. It's known but random. That's the task of boson sampling. And now we have to ask the following question. Can the classical computer efficiently simulate the distribution of the output mode numbers? So can we address this problem with classically? And the answer is no. Why is no? Because there is a very long paper, 95-page paper, which showed that if this was possible, you would have some very strong impact for the theory of computational classes. So this requires a very formal demonstration. But I can provide you an intuition on why this is hard to be performed classically. Because when you have n bosons, which are indistinguishable, that propagate, you need to symmetrize over function because the particles are indistinguishable. And one may ask, how many operations should I carry out classically to symmetrize over function? If you have n particles, you need to do n factorial permutation. So if you want to calculate one transition amplitude from the input to the output, this requires something which scales exponentially, and that's where the complexity is coming from. This is a physical argument. Let's move it now in a mathematical argument. If you want to estimate the propagation of n bosons over m modes according to unitary evolution, which is uniformly drawn, the transition amplitude from one input state to another to an output state, this is related with the permanent of a squared matrix. The permanent is something which is very similar to the determinant. So the determinant, we know, if you have a squared matrix A, B, C, D, the determinant is AD minus BC. The permanent is AD plus BC. Each time you take a permutation, you keep the same sign. Determinants are used for fermions, permanents are used for bosons. And now what happens on an archive should, but that's really, there are a lot of technicalities that I'm jumping now, obviously, is that the permanent is something with a complex coefficient, is something which is extremely hard to estimate with a classical approach, not only the permanent, but also the approximation of the permanent. To make the long story simple, this is classically hard. And to come back to Rene's question, this is classically hard, not because I've taken one algorithm. This is classically hard for a very deep demonstration. If this would have been easy classically, this would have a major impact on computational science. Now, this tells you about the scaling, which is exponential. Another question is now, what is the best heuristic algorithm to carry out this classically? And that's a more open question. To summarize, boson sampling is hard classically. Let's do it with a quantum approach. There is a question by Luigi. Please, Luigi. Sorry, Leandro, I'm jumping in, but I could see on my screen what's right at the end.
You're muted, Luigi.
Oh, okay. Can you hear now?
No, you're muted. Yeah.
Yes. Now here. Quick question on how you prepare in the input state. Okay, in the sampling. Basically, I understand that basically you send photons in all channels, right? At the same time in different channels.
Yes.
Am I right?
I'm going to clarify this in a couple of slides.
Okay, thank you. Thank you.
Thanks, Luigi.
Okay.
So this is a summary.
We have another question by James. Please go ahead, James.
Since we're interrupting, I thought I'd jump in at this point and interrupt as well. Hi, Fabio.
Hi.
So I'm sure you're possibly going to go on to answer this, but I'll ask it now anyway. Can you comment on this idea that boson sampling is, obviously it's classically hard when it's at large scale, but there was this result back in 2018 that suggested that noisy boson sampling could somehow be efficiently simulated by breaking it down into several smaller, effectively smaller graphs, right?
James, I will come back to this later on.
Okay.
I have
No
a side on the open challenge, but the question is excellent.
No worries. Sorry.
I'm
Okay.
gonna go
I
back
thought
to
that might
this.
be the case. Yeah. Okay.
Thanks. I keep this for when 2 slides. So now let's see a bit how you can implement boson sampling with a quantum hardware. You need n photons, which must be indistinguishable. You need m modes. You need to send the n photons inside the m modes. And the M modes need to implement your evolution. You need to have a very large interferometer, which is highly concatenated. How do we implement this? I will after discuss how we implement the single photon states, and we now focus on how we implement the circuits. Because now we go back, we have boson sampling, we go to photonics, and I would like now to open a parenthesis on the technologies that we have been working on in collaboration with Politecnico di Milano and CNR, also because this may open some possible ideas. So now the question is, how can we implement this unitary transformation? And this is a very large interferometer. The idea is to have all these devices implemented in one chip, in order to have something which is inherently stable, in which you can elaborate information. The approach which is taken by Milano, with which we have a very strong synergy, is to fabricate waveguides which are embedded inside the material. So you take a piece of glass, you tightly focus a laser inside the glass, you move your sample, and then you get a kind of multiphoton absorption, which leads to a change of the index of refraction of the material. So you get a waveguide which is really embedded inside the material. Then by moving the sample, you can get arbitrary geometry. So this gives you, not this one, this gives you a video which shows you how the writing process is happening. You see a substrate, which is glass, you see a microscope, you focus the laser from the top, and where you see now a white spot in the video, this is the plasma which is inducing the change of index of refraction of the material. This is how you fabricate your waveguides embedded inside the device. And then you can now, you see, that's an animation which gives you an intuition. You move your sample, obviously you need to have a very high control on all the direction, and then you can move different, you can get a geometry pretty much flexible on your device. I would like to show you a bit what device do we have realized in the last few years. So the first one, it's a beam splitter. So the first ingredient, it's called directional coupler. You take the two waveguides, you browse the two waveguide closer, and you get the coupling via the evanescent field. Then you can get many of these devices concatenated, and for instance, you can implement logical gate. Or what is shown here, you can have many beam splitter, many phase shifter, and you get a multipath interferometer. And this apparatus was implemented to realize Anderson localization. Then we had other devices like tunable wave plate on the chip, but all these devices I'm showing you were like static device, in the sense that once you fabricate it, it stays forever, at least 10 years. That's what we check it up to now. So you have your structure, it's there, it's on the chip, it's stable. What you would like, however, is to have the capability to reconfigure your device. And this was introduced, I would say, in this laser writing approach only recently by Milano. So it is that you see, you have this animation, you have the waveguides. You have a waveguides, you have some thermoelectric controller near the surface. You can locally eat your waveguides, and this will change the index of refraction. So while this approach is pretty standard with other platforms like silicon photonics, silicon, this was never done before with laser writing. And now you have a kind, this is, if you look to this picture, you have a 6-mode interferometer, you have beam splitter, phase shifter, beam splitter, phase shifter, and so on. And then the first experiment with this was done on 2015 with a phase shifter, only one controller. Then we did more phase shifter, or did some kind of programmable simulator, And recently, we also integrated a source of entangled photon pairs. Then another possibility that you can exploit with this structure is to realize devices which have a three-dimensional geometry. For instance, this one is a treater, where you have three modes which are in 3D scheme, and you can combine them. And then you may have more complex infrastructure. And today, I will, at the end of my talk, show you our first 3D device, which is also programmable. That will be the final point of today's presentation. I'm wondering whether there is a question by Luigi Amico.
You are muted, Luigi. Yeah. You are muted, Luigi.
I can wait. I can wait, Fabio.
Yes.
Okay. No, my question is whether this reconfigurable circuit can be done in the course of the same experiment.
So in this case, the reconfiguration is pretty slow because it's a thermal effect. This means the time you need to reconfigure the device is seconds, dozens of seconds. So you cannot act on the same photons. If you want to have fast switching, you need to have electro-optic modulators. That's not the case. So in this case, you change the functionality, and this requires physical. Obviously, you can have in mind you perform an experiment and you reconfigure it, but this will never be on the same RAM.
Okay. Thank you.
You're welcome. Thanks. So, and now this was to show you the platform. Now we are back to 2013, and I would like a bit to show you the history of boson sampling. This was the first boson sampling paper. This was the paper together with our friend in Milano and our friend also in Rio, Ernesto Galvao and Daniel Broad. But there were like 4 simultaneous papers you see in different places. What was the initial point? It was boson sampling of 3 photons over 5 modes. The 5 modes were implementing this sort of structure, which is a unitary transformation acting on your photons which are propagating. And then, as I told you before, you can implement your chip. So I would like now really to show you, I have a video, really also to answer Luigi's previous question, or Rene's previous question, I guess, on how we were implementing in terms of input photons. So let me show you this really step-by-step video, really of 2 minutes, which tells you how we did these first boson sampling experiments. So at that time, to generate single photon, we used parametric down conversion. So we generate photon per pairs. We pump a nonlinear crystal via UV pump beam. The UV pump beam excites nonlinear crystal. You create pair of photons. In this case, we create 2 pairs of photons. We create 4 photons. 1 photon is kept on the upper side as trigger. The other 3 photons are coupled to single mode fiber, injected in single mode fiber, properly synchronized, because you want to have indistinguishability, because you get something which is hard to calculate only when you have indistinguishability between the particles. In this case, the photons are the small wave packets. Then you need to synchronize the 3 photons. You synchronize the 3 photons by having some delay lines. Typically, in this case, it was something like 200 femtoseconds. You inject again in single mode fiber, and you can inject an integrated chip. Now, your chip in this case was maybe a 11 modes chip. So you have in this case m equal to 3, m equal to 11, and you see the photon splitting. This is only a way to represent the superposition. So you see that's your initial state. You will have here the evolution, so interference between the many paths. In the output, you have 11 modes. You have the fiber arrays, many fibers, which connect all the output modes to an array of single photon detector. Now, the single photon detector can count 0 or 1. And then each time you run the experiment, you will project the output state on some contribution. And this is where you are sampling from the output state. This is a boson sampling. That's a sampling of the output distribution. So what is the result here? The result here is a sampling of events. In this case, 3 photon, 11 modes, And then you get the string, which is a string of 1 and 0. In that case, 3 photon, 11 modes. And that's boson sampling. So if you look to the lab, this was our setup that we adopted in the 2013. Then I will show you a bit what was advanced globally on this framework. You see a photo of the chip here. You see how you inject in and out from the chip. And this apparatus is a bit more complex because this is the picture, the upper side, is the experiment adopted to carry out scattershot boson sampling, which is a kind of variant of boson sampling. That's the second generation where you can see some reconfigurability, but I will show you our last chip later on. Now, what do we measure when we have boson sampling? This was a result by 2014, now it's 2 years ago, but this only to show you how was the trend. You can see in this case, you have 3 photons, 7 modes, 3 photons, 9 modes, 3 photons, 13 modes. In this case, the Hilbert space is pretty small, the Hilbert space dimension, because if you have n photons over n modes, the Hilbert space dimension is a binomial coefficient n plus n minus 1 n. So in that case, it was 300. This means that the Hilbert space is small, and at the end, you're also able to reconstruct the probability of your output state because the Hilbert space is fully manageable. You can measure all the probability, and you can, that's the blue side, and the orange is the classical simulation. So there is no quantum supremacy here. Even the classical hardware is much, 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 much faster than the quantum one. And we also thought that this picture of the boson sampling is not conveying you the right intuition. Because when boson sampling becomes interesting is when the Hilbert space is huge. And when the Hilbert space is huge, you will never measure the probability because you will need exponential experiments to measure the probability. You are only measuring a set of sparse events in a huge Hilbert space. So I don't know if there is any question now.
No, Fabio, this is going great.
Okay.
Go ahead. Yeah.
Thanks. So this is, I want now to show you an evolution because my goal was really to provide you some our picture on how this field is evolving. 2013, you had the first experiment, and then you had a set of experiments by many groups worldwide with different sort of contribution. We implemented scattershot boson sampling, which is a variant of boson sampling, which is more bright, in the sense that the quantum side is much more efficient. You had, for instance, boson sampling carried out with the first reconfigurable circuits. This was done in Bristol. Then you had some first paper. You had the first paper, which was a simultaneous paper by Andrew White and Pascal Snellard, Australia, France, and on the other side, John Welpine in China, where they could do boson sampling with a quantum dot. And with this platform, they pushed a lot the apparatus. And I would like briefly to comment their scheme. What they had in their case, they had no more parametric down conversion. They had a single photon source, which was able to generate single photon on demand along a given mode with very high indistinguishability and all divided by a fixed timing. That was the pulse rate of the laser. So you have the stream of photon all along the same spatial mode, but different temporal mode. And then they have here what they call the demultiplexer, which is something which is transferring the string of photon from different times to different modes. And then they could inject all these single photons in a fiber array that was going on a fixed, low-loss photonic sequence. And thanks to this approach, they could really largely increase the number of photons that they could send in the device, and then they can really increase the dimension of the Hilbert space of the device. That's the Hilbert space dimension. Let me comment that we are also now setting up this sort of apparatus in Rome. That's something that we are now preparing for the next year, only as to share this information for potential collaboration. Something that's different is that they had no integrated circuit at the center, but they had a bulk device which was very low loss with many modes but no reconfigurability. This means the device was fixed. This was in 2019. We gained no supremacy. So what is the challenge now with boson sampling? That was a challenge 3 years ago, and that is a challenge nowadays. On one side, you would like to improve the photonics technology. You would like to have more photons, more optical modes, alternative schemes. You would like to have single manipulation on chip, on large chip. Then there are some open questions. Is there some hybrid scheme of boson sampling which are more suitable to demonstrate quantum advantage? How can we increase the complexity? And what is the impact of noise and imperfections on the hardness claim? And now I'm finally back to James' question. What happens when you have partial distinguishability? And you have the following recipe that when you have partial distinguishability, if you send n photons, your output state will be a kind of combination of having interference between 2 photons, 3 photons, 4 photons, up to n photons. And the weight of the contribution with n photons decrease when the distinguishability decreases. This implies that if you have a low distinguishability or not high enough, you can efficiently approximate your output state only by considering boson sampling with a much lower number of photons. This means that this makes classical simulation easier because it's a sum of many perturbative approaches. And this means that if you want to have n photons and make the job harder for the classical counterpart, you need your distinguishability to be very high. I don't know, James, if I addressed your question. I guess this was the point.
Yeah, that's more or less what I was asking. I guess I was more. I guess at the time I was just asking that, but now I'm curious about your perspective about whether this is achievable with a parametric system and a series of waveguides, or whether kind of fabrication imperfections and stuff will make this hard as you try and scale it up. I mean, the Chinese groups use these super low loss kind of integrated devices, I think partly because they didn't have any, well, it was easier to kind of control path length differences and similar in those things, right? But I guess also the quantum dot's beneficial as well, right? But
that's something on which I will also come back. So okay. I will say something that nowadays the trick of the quantum dot here, as you see, is to use the same quantum dot. So why it is harder to have good indistinguishability between different quantum dots by using the same sources. Now you can have very high indistinguishability relying on the same apparatus. So we say that the indistinguishability from this perspective is nowadays pretty high. It can be larger than 95%. And higher values, that depends really on how much you engineer the control of your device. I will then come back to your question. Now I will really cite the papers that you were mentioning. Leandro, may I ask you how much time is left, more or less?
You started at 7, so like 15 minutes.
Okay, perfect.
So, yeah.
Okay, that will be, so now let me change now the next step and comment what are the different variants of boson sampling. And there are 2 reasons on why one is interested in studying different schemes of boson sampling. First, we would like to find a scheme which makes the job easier for the quantum side and harder for the classical counterpart. Second, different variants of boson sampling may have different connections with some quantities that you may sample from, and this may have some, may be useful from some algorithm with some hybrid approach. So, in the standard boson sampling, you fix what is the input as shown here. The 3 photons are sent here, and you have a unitary transformation. When you talk about scattershot boson sampling now, what you have is you have a fixed unitary transformation. You have an array of 2-mode squeezed vacuum, which means parametric down-conversion. You have an array of these sources. You take 1 photon of each source as a trigger, and you send the second photon in the chip. And you may have as many sources as input modes. Each time you run the machine, the different detector here will fire. So this means that a different set of sources will generate your photons. This means that each run of this experiment, you are performing a standard boson sampling with the different input states. So that's a bit technical, but the intuition is that this approach allows you to exponentially increase the brightness of your quantum apparatus. You need many, many parameters on conversion, which fail your unitary. We did this with bulk optics, and last year this was also realized by Bristol using a chip, where they had many, many sources on the chip. And they will comment to answer James, when you fabricate many, many sources on a chip, pretty much it has the same quality in terms of source and so on. So if you're able to engineer a source which give you a wave packet with a good quality, when you do many, many millions, the same device, due to the control capability on the writing process of your waveguides, the sources are not much affected. So when you typically go on chip, the variability of the sources that you may have is not significant. So there was a question by James, I guess.
Sorry, just that's fascinating. So I guess you had way earlier in the talk, you showed a quick cartoon of a scheme where you had on-chip sources as well. And if I'm right, basically you had a laser-written waveguide chip that was splitting up your pump beam, and then you had a bit of some kind of pulled material, and then that fed into another laser-written chip, right? So do you? Oh, exactly. Yeah, this one here, right? The bottom right image. So in this one here, I see now. Yeah, the pipelin has some lines through it. So are you producing waveguides inside the cartoon material as well, or are you? So like, how is that working?
This source was not adopted for Boson sampling in that case. So, but what I can tell you, so in this case, what we are doing, we first have the central chip. It's lithium niobate with periodically polling, and we write the waveguide on that. But the quality of the waveguide here was not so high. So the losses are typically higher in the central part than in the other chip. But what I can tell you is that this was a bit lossy, but the indistinguishability between the two waveguide was almost perfect.
Okay, that's fair. So that was my thinking, was that I know that direct written waveguides in crystalline substrates tend not to be very good. So my intuition was that they wouldn't be very good at indistinguishability, but it's interesting to hear that they were. So it's cool. That approach could scale, right? You could do that for boson sampling, you think?
Yeah, but on your side, you are correct, because the quality of the waveguide was not so high as in the other media. This is why we have larger losses. Okay. So your comment, I would say, is correct, that it's more complex when you apply these techniques in crystal, and we could see that. So that's the quality, that's something which we are now coming back together with Milano. This was the first generation. We are working on that. But also there is space for improvement. But here we could carry out some, you could use this also to create null states, and the distinguishability was very high.
Okay, thank you.
In the sense that the spectral property being the same, essentially these two have a distance of 50 microns, even less. So the polling is the same. So the spectral property, you have to imagine that if your waveguide is not very good, you are adding losses, but the spectral characteristic of your B photons is almost the same.
Okay, yeah, I see.
Thank you. So now we come back to this slide. I commented you scatter shot, and this was the preliminary step before the Gaussian boson sampling, which was the experiment carried out by John Repan to demonstrate quantum advantage. This is a variant of scatter shot. What happens? You have now a single mode squeezer, so you create pair of photons along the same modes, and you see you inject in Gaussian boson sampling the unitary, all the output state, all the squeezed vacuum. Why is Gaussian boson sampling interesting? Because now you inject Gaussian boson sampling with squeezed vacuum. This means that the average number of photons that you inject can be much larger than in the previous scheme. So you can inject in your device, on average, almost 1 photon per mode. So obviously, the number of photons is not fixed because it's a squeezed state, but the average number of photons can be much larger. One should be careful. It's a squeezed mode vacuum, so it's sensible to the phase. This means that here you need a phase relation between the generation and the device. This was then the paper. We are now in December 2020, So it was 4 months ago, and that's a paper by John Wepan, which from my point of view is really impressive. They could really explode the hyperspace dimension. They had 50 input single mode squeezed states. This was not integrated, it was bulk optics. They had 100, you see that's a picture of the apparatus. You may see at the center the device which is coupling 100 modes. So it's really an impressive experiment that you can summarize, one could summarize in the following way. You had Gaussian boson sampling, so I repeat, your input is a single mode squeezed vacuum states. The squeezed sources were realized with the bulk optics, with a PPKTP crystal. They pumped 25 of them, and each one was realized in 2 squeezers. You need to send all this light inside the low-loss interferometer, which was bulk. You need to stabilize all the different paths. More precisely, they had 50 modes, and then they could use the 2 polarization, and then this leads to 100 modes. So they used 1 spatial mode with 2 polarization. These are some small technicality. And then they had 100 superconducting nanowire single photon detectors. That's a scheme of their apparatus. It's not trivial, as you may see. It's impressive. Why they use it? So they could obtain a good indistinguishability, but now the key, one open point that in their case, this unitary transformation at the center was not reconfigurable. Instead, that the unitary was fixed in their problem. I would also like to mention, since I'm really trying to provide you a picture of what's going on, this paper starts in Nature 1 month ago by Xanadu, and this was fully now on chip, so you see a different approach. Everything is done on chip. On chip, you have squeezing sources, filtering, interferometer, and quantum output. In this case, if I'm right, they had 8 modes, so you see the mode number, but it was reconfigurable, and also the number of detected photons was much more reduced compared to the Chinese one. Now, I would like to jump some slides to show you what are our last results, what we are doing now in this direction. And it is the following. We are now working on 3D boson sampling, where we would like to have a 3-dimensional geometry of our apparatus. So to exploit laser writing, 32 modes, 3-dimensional architecture, a continuous coupling. This, because you would like to have minimal losses, and also having something which is 3D allows you to have more coupling between the waveguides. And so analogously to a 2D quantum circuit with qubit, you need to have less depth to have a full interconnected dynamics. That's a picture of the apparatus. You see the sources, the generation, and we come back to this later on because I have a better picture. So, what is interesting, this is the chip. You see, you have the 32 modes. You come in with the fiber, you come out, and in the output now, you have a squared fiber array, and you can connect with a squared fiber array on the output. Now we have 32, but we already plan to go to 64 within a short time scale, and you get the coupling. You see, but now, up to now, in what I told you, everything is fixed. This means that this device is creating one unitary transformation. Now what you can do, you have this unitary transformation, you need to characterize the unitary operator, so you have to do many measurements to characterize it. And what is interesting is that now you can characterize whether your unitary matrix is random hard, so you can investigate what is the distribution of the phase and the amplitude. But what is interesting really is to show you that now we have reconfigurability. So you have this 3D layout that's shown here now. You can have many thermal shifters on the surface that are locally eating from different distances systems. And what you can see here, I don't know if you see this, you see the spot which are changing when you change the different temperature. So this, only to give you an intuition, that now is also a device, you see, you can control the different phase, and this local change will change your unitary transformation. And what we have characterized now is when we change this parameter, how much are we spanning the set of unitary transformation? Are we localized in a subset, or are we able to realize a random R matrix? And that's what you see here. I'm brief on that. This is theory when you have random R distribution. Blue are our data. You see, we don't get something which is really random R, but we are not far away from getting something which has distribution of random R. So having this control phase allows us to move somehow randomly in the space of the unitary transformation. Leandro, may I ask you how many times is left?
Let's say 4 or 5 minutes maximum to keep it.
Okay. So
if you can.
That's perfect.
It's very interesting. It's fascinating what you're showing. Yeah.
I wanted really to show you the framework, but also what are our capabilities in the lab today, because this may be eventually of interest. And then a key point with boson sampling is the validation. Is there a way to validate boson sampling? And that's something on which also Leandro did some pivotal contribution. And the key point is that when, for instance, you factorize a number, you get a solution, you can easily check whether the solution is correct or not. But you cannot do the same when you address something of quantum simulation. And on this side, boson sampling can be an interesting benchmark because you can try this certification technique that you may then imagine to expand to other quantum simulation tasks. So we're working on that. I'm here only reporting some paper from Rome. It's not exhaustive, but you may try to validate with different approach, but your validation will never be a conclusive one. This will be only to provide you a strong evidence that everything is going as expected, but it's not the final answer. You will never know what you did is exactly what you were supposed to do. And this argument also applied to Google paper and also applied to Pan paper. For Google, they use the cross-entropy validation. For Pan, they use the other one. But the key point is that when you enter in this regime, at the end, you are only providing a growing evidence that everything is going as expected, but it's never the real final demonstration. That's also what we implemented with the 3D boson sampling that I've shown you. This is our last week results. So this is our first experiment post-lockdown. And but this says that everything is going as expected with the tool capabilities that we have today. So what I've told you was why is boson sampling may be interesting, how you can implement it, what are the open challenge. Something which I could not discuss was also the paper by Google, which was also been doing quantum supremacy, but with a different framework, different feature, different validation techniques. But the reason why I believe this is a very fascinating field, here I'm summarizing comments from others, that this experiment really combines computer science, physics, and quantum engineering. Now that's an open question is, can we carry out some interesting task with boson sampling? And that's something on which a key player working today on Gaussian boson sampling is a company Xanadu in Canada, who have now a whole team devoted to this. I'm here citing some of their paper. They're really trying to figure out whether which kind of algorithm may exploit Gaussian boson sampling as a subroutine, and that's a citation of some of the paper that we are currently investigating. So I guess this is everything. So I would like to thank you for your attention. It was a great pleasure, and I really hope to meet you soon in the same room. Thanks, Leandro. Thanks to everyone.
Thank you, Fabio, very much. This has been a fantastic talk. Thank you to the audience also for the questions. It's really great to see such a discussion about computational complexity in the words of an experimentalist of your degree, so to say. So there have been already some questions during the talk. So I will read, there is one question. We have time for just a couple of questions, so as not to make it so long. There's a question by Sergi, and the question is the following one, Fabio. I will read it out. He said, how does the 3D structure of the chip impact loss and noise with respect to the standard 2D chips? So how does it change with losses and noise when you go from 2D circuits to 3D circuits? Can you
Thank you for
comment
the
on?
question. So I guess the loss are lower. The reason is that we have here this direct coupling, and essentially we can have a coupling between 32 modes with a much smaller chip. Having a much smaller chip, because it's more interconnected, we have lower losses. With the previous approach, we would have needed a chip much longer.
Interesting.
So that's really changing a lot in the game. So, and what was missing with the 3D was reconfigurability, and this is why we don't have a full reconfigurability. Today we have 16 parameters, but the fact that we can generate unitary with just enough random leave us the hope to exploit it as a complete tools. Concerning noise, again, it's smaller. At the end, typically, when you go on chip, you don't have any decoherence effect. Because you are not adding any partial distinguishability. Nothing is fluctuating because you are on chip. The only point is losses, and also how to combine losses with reconfigurability. And this is what I hope to have provide you at least an highlight on what we have been doing.
There is, thank you, Fabio. There is another question by René. René, please go ahead.
Yeah, thanks a lot. I can only agree with what you said. Fantastic talk, fantastic work. Yeah, so following up to this to the 3D question, so you showed this Dritter, right, where you can like combine now like a triple beam splitter. And so what I was wondering now is, of course, you get a certain output state. Then could you then like mimic or map this what this Dritter is doing in a 2D system, or is this not possible? And of course, yeah, and of course you can then also, of course, I can go on and ask if I have a quadrupler or whatever n input modes, could I then, yeah, exactly this Dritter, for instance, yeah, could I mimic this then with a 2D chip, or is this not possible?
No, indeed, you are right. You can fully, any of this transformation can be mapped on a 2D layer, but the 2D layer to implement the same transformation would require more depth.
Okay, makes sense. Understood. Super. Okay.
So you can carry out the same unitary transformation, but you can save a lot of resources in terms of depth. But you can map.
Fantastic. So let me ask another question about this, the reconfigurability, right? So like you do this to have more freedom in terms of random matrices to implement. And so, but of course you could, why is that so important? Because you don't have to print that many circuits as unitary gates that you implement, right? It's a more like fabrication advantage that you get, right? There is a technical thing, right? Or did I get it right?
Yes, but I would imagine that, Leandro, you call me, you say, Fabio, you have to do race to demonstrate quantum supremacy. Take this unitary sample from it.
Right.
Yesterday I had to phone Milano. Milano, please make the chip, do the chip, take the train, and we start the experiment. Okay, that's hours, that's days. Now, in principle, not fully, we can, you give me the U and I can at least go nearby this U and start sampling from it.
Fantastic, fantastic.
I don't know if I clarified. It's
yeah. No, it's definitely, it's certainly in terms of practice, yeah, practicability. So we have a last question, and this is James. Please speak up. Thank you.
Hi. Yep. Okay. Thank you, Fabio. It was a really interesting talk, and I think you did a really really detailed and kind of honest job of presenting the boson sampling thing in general. I have a question, a technical question about your reconfigurable 3D waveguide arrays. So I guess it's a two-part question. The first part would be, I guess if you have a sort of number of electrodes that you can sort of decide to apply a current to some of them or some subset of them to create like a thermal field, right? how reproducible is that? As in, if you create a particular random unitary, and can you then return to the same settings a few days later and sample from a similar unitary, or is it like really hard to reproduce that kind of stuff? And then I guess my other question was just, do you have any other ideas for making a more controllable, reconfigurable 3D structure like this?
Thank you so much. So we have the replicability of the if you applicate the same voltage. Up to now, it's something that we are still investigating to see how much is stable after days and so on. That's something on which we are working. Also, the following step is to have some kind of calibration like machine learning, but that's something which is for the future, where maybe you can map your control parameter on the unitary. So on the stability, something that we are still working on. So that will depend really on the connector and on the power that you dissipate. I cannot tell you all the detail, but this approach is still in development in Milano, and they're finding a way to obtain less dissipation during the thermoelectric, because the lower is the dissipation, lower power you're putting in the system, and higher is the stability. What I can tell you is that typically we have carried out was the same thing also lasting 4 days, and after 4 days we have the same unitary transformation.
Okay.
But the key today, one of the key goals is really to have less dissipated power, because less dissipated power you have, more controller you can put in your device. And that's something on which we're working.
Fantastic. This is amazing, Fabio. Congratulations for the fantastic work that you guys are doing. I'm very happy to see this news about reconfigurability. This is really a huge improvement. And thank you for such an excellent talk. This has been useful to all of us, theorists and experimentalists here.